everybody know Stacy? Maybe she can introduce herself a little bit.
Hello, everyone. Thank you for coming. I know travel is very difficult, so I really appreciate everyone coming here to join us. For the next bit of time, we're going to be having a panel of researchers. There'll be 3 different groups that will come up that are doing different things in their labs, so they'll be able to offer different perspectives and different approaches that they're trying. They'll explain a little bit about what they're doing, and then what we would really like is to have an open discussion with all of you. So please have your questions ready, and we just would really like it to be an open dialogue for everyone. So first up, we're going to have Jenny and Becca. Come on up, ladies. So I'll pass the mic to you. Jenny and Becca are with the Lawler Lab. Dr. Mike Lawler is, a lot of you probably know, is really involved in Nemaline myopathy research and myotubular myopathy. These ladies are going to talk about what they've been working on in the lab. So would you like to begin, Jenny?
Hi, I'm Jennifer Tinklenberg. Like Stacy said, we're with the Michael Lawler Lab, and I'm sure I don't need to introduce Nemaline myopathy to anyone in this audience, but just as a brief kind of statement, it's related to 13 different gene mutations, and there's severe heterogeneity between the mutation and the severity of the disease. So for a long time, everyone's been focused on...
It's really hard to hear.
Closer? Ah, there we go.
Yeah, like,
Sorry.
Can you turn it up in the back at all?
Yep, I got it.
Oh, yeah. We did have, I don't know if it matters, we do have a PowerPoint or a PDF of our posters. Okay, that works too.
Is that the right one?
We can go off of mics too if we need it. That's fine. So we do have 2 posters out in the back as well, or out in the hallway, I should say, in case anyone wants to look at those. But just to start over, Nemaline, 13 different gene mutations, very heterogeneous. So everyone's mostly been focused on the different genes themselves. So we've in the past done a lot of research with myostatin inhibition. Excellent. Thank you, Rebecca. So in the past, we've done a lot of research with myostatin inhibition. We're both 2nd-year grad students, so we're just starting our PhD projects. But when I first started with Mike, it was about 5 years ago, and I was a technician in the lab. So we did myostatin inhibition. If you don't know what myostatin is, it's a small molecule that basically tells muscle when to stop growing, when it meets the body's metabolic and energy needs. So with myostatin inhibition, you're basically telling the muscle to keep growing. The idea was, even though we weren't fixing the primary problem with contractile dysfunction, with the Nemaline rods and the general disorganization of the muscle fibers, we could potentially make larger muscle fibers and therefore more contractile elements. So that was the thought, that was the rationale, and we tried it in 3 different mouse models, the ACT1 H40Y, the ACT1 D286G, and the conditional Neb knockout model. So when we did it in the H40Ys, we noticed an increase in muscle size, we noticed an increase in muscle size between, you're looking mostly at the green and purple bars, increase in muscle size, but no functional increase in strength. When we did it in the D286G mice, we also noticed this increase in muscle size between the green and the purple bars again, and we noticed an increase in strength to wild type levels that were also treated with the myostatin inhibitor. However, when we did it in the Neb conditional knockout model, there was no increase in muscle size, and there was no increase in strength. So this really, Alan?
Sorry, finish your sentence.
Okay, so this really kind of told us that we needed to take a step back because there's something going on even between the different mouse models that isn't acting the same between the mouse models. So from that, we kind of wanted to take a different approach and look at secondary functions of the disease or secondary processes that are in the disease that then potentially could be the same or similar as a treatment target across mutations. So then we're not treating each individual mutation, we're just treating a secondary process that's in common.
Could you just explain for a sec what ACTA and NEB are and what H40Y means?
Sorry, I woke up this morning, my voice was not the best. So the ACTA is the actin gene, so it's mutations in the ACTA gene, and this H40Y is a point mutation versus a D286G point mutation. So at area 40 or position D280 or 286, it switches one amino acid to create a very small change in how that actin is formed. So in both models, the H40Y and the D286G, the actin actually binds, like each actin subunit binds closer together than it's supposed to. The problem with the H40Y people and animals is that that binding of the closer subunits causes those filaments to be completely inactive, so they do not work in the muscle. With the D286G, it'll actually form these heteropolymers, so there'll be both wild type, normal actin, as well as mutated actin, so they half work. So with the H40Y model, you end up with only about half of the fibers being functional, and with the D286G model, you end up with all of them being slightly less functional. So H40Y can be a slightly more severe disease, and we see that in, and I say that because, again, it's very variable, but with the mouse models, these mice look worse than the D286G mice. The conditional nebs, they actually start with a lot of nebulin, and then as they age, it decreases over time, so they end up losing it. When they're in the womb and when they're fetuses, it's one form of nebulin, and as it transitions to the adult form, it slowly deteriorates as it gets replaced, because it doesn't get replaced because it's knocked out. So these animals, by the time they're about 5 weeks old, they only have about 5% nebulin left.
So as Jenny said, I'm Becca, and I'm going to talk a little bit more about recent stuff that we've done in the lab, and then what our PhD projects are going to focus on for the next 3 years. So as Jenny said, the treatments were very variable between models, and so we wanted to look at secondary processes. And so as these, yeah, I know these aren't our slides, so it's fine. As Nemaline is in part a disease of protein aggregation, we decided to look at protein expression across the mouse models that we do have. So we isolated skeletal muscle from the 3 mouse models at early and late stage of disease, and then we sent it to one of our collaborators who did proteomics analyses on these. And so what they did was identify the proteins and what level they were present in each model at early stage and late stage of disease, and then compared it to the wild type to see what was different in these animals. And so we identified, I don't think it's up here, but we identified around 1,200 proteins for each of them. So these are really big data sets. And so I got all of this data back, and I ran it through what's called ingenuity pathway analysis. And so what this does is it looks at the changes in protein expression to see what pathways could potentially be dysfunctional in these models. And so our major focus was to look for common patterns across the models. And so one of the major things that we saw was that the mitochondria, or energy metabolism, was affected across models. So at early stage of disease, mitochondrial dysfunction came up as a top process that could potentially be affected. And then at later stages of disease, it was only there in the most severe models. So our general thought right now is that mitochondrial function could ramp up at the beginning of disease because you're working so much harder, your muscles aren't contracting properly, and then it kind of crashes out at later stages of disease. And so what we are going to work on for the next 3 years of our lives essentially is I'm developing cell models of Nemaline myopathy in order to look at if mitochondrial function is affected and if this could be a therapeutically targetable process. And so I'll be looking more at the biochemical aspect of it, while Jenny will be looking more at the whole animal part of it. I don't know if you want to say any words about your mouse.
Yeah, so Becca's looking, like she said, at cells and the molecular processes, but I'm going to be taking the whole animal, and most of my projects involve isolating the mitochondria and then looking at how those isolated mitochondria from the animal tissue work. So I've already kind of seen some differences. I don't want to get too cart before the horse, but but there could be some potential functional differences that might be promising. Well, Mike doesn't have the D286G data up here, but the D286Gs show, I'm talking about total mitochondrial function. They don't show any differences in mitochondrial respiration, is what it's referred to as, but the NEB conditional knockout model have this decrease in respiratory function. And that respiration is basically what is making the ATP that is powering cells for activity. So the ATP, every cell needs ATP. That ATP or energy comes from the mitochondria, the powerhouse of the cell. And without it, you end up having the fatigue and the tiredness and relying on some other metabolic processes. So in essence, hopefully all of this, either biochemically or functionally, will be able to target some other element that, if nothing else, might be able to increase energy that then might be able to allow the muscles to function better. It's not going to fix the primary contractile problem, but hopefully it will at least improve quality of life to some degree.
And so this is something that we're hopeful about, making good progress in the next 3 years as other people continue to work on therapies that would help the primary genetic cause. And we are very grateful to AFBS as they have funded all of our project thus far. And with that, we'd like to open the floor to any questions you guys might have.
My name's Josh Engelian. I'm from Toronto. My youngest daughter, Gabby, has NEB, form of Nemaline myopathy. I just had, maybe it's more of a basic question, because you were talking about early stage and late stage, and I don't know if that's just specific to the mice models. And so my question was, I always understood that Nemaline myopathy, unlike some of the other neuromuscular conditions, was not progressive, other than maybe the respiratory symptoms as people get bigger and need more respiratory needs. So could you just clarify that for me, if there's a distinction in people between early and late stage?
Yes, so it's not necessarily a traditionally progressive disease like the dystrophies are, but as the body gets bigger, by default, people get heavier. And so even though it's not progressing, you still end up seeing a progression. So people still have a harder time doing things just because their arm is heavier, so it takes more to lift their arm or lift their leg or whatever the case. So even though the muscle itself isn't particularly changing over the course of the disease, that's where you see the loss of ambulatory function as you get bigger, because it takes more to lift your body and keep yourself upright versus when you were 2. So that's really the difference. With the mouse models, the conditional Nemaline mice, we do see more of a progression because, like I said, they start with a lot of Nemaline. So when they're little, they look almost normal, and then as they age, they deteriorate. So none of the mouse models are perfect models for the human disease or a perfect recapitulation of the human disease, but they do give us something to work with, which is, again, better than nothing. So it's also something that we need to keep in mind when we talk about any of these things, is whatever we find in the mice, how does it translate to the people? Which is where I guess I'll put in a plug for the tissue repository.
Yeah, thank you.
So our lab also has a tissue repository, which maybe Stacy can say something about as well, where you can submit tissue samples or whatever the case, and then that allows us and other researchers to, whatever we find in the mouse tissues, go to the human tissues and potentially see if it matches. So
Exactly. Thank you. That's a really great opportunity. I didn't say anything about that, but just briefly, for those of you who don't know me, I'm Stacy Cassette, and I've been working with Dr. Mike Lawler since 2012. We were approached at that time to launch a tissue repository, a place to centralize human tissues that could then be transferred to research labs anywhere in the world, for our researchers to have access to human cells and human tissues in order to test their theories. I am able to consent anyone for this program here today who hasn't already consented for participation. It's a very simple process. I go through it all with you. If you've had a muscle biopsy in the past, we can bring that tissue in. If you have an upcoming surgery, we can talk about how that might be an opportunity. So the message is, consent early so that we have the paperwork done, and then we work out, when and if there's an opportunity for your tissue to get centralized at our repository.
Thank you, Stacy. And hi, I'm Alan Begg. So if I could also just expand and comment on that. Two things. First of all, in terms of the mice, Jenny from Helsinki is also an expert in this area. Maybe you'd like to comment on that in a minute. And then I just saw Laurent Servet from Paris, actually now Belgium, walk into the room, and he'll speak to you again in a few minutes about natural history and establishing that, which is very important. And here in the US, Jim Dowling, actually, who's in Toronto, Canada, together with Karsten Bonneman and myself, and a number of MDA clinic directors are planning a natural history, prospective natural history study, focusing on everybody with Nemaline myopathy, and in particular folks with actin and nebulin mutations. And so you'll be hearing about that. It's going to be done in collaboration with CureCMD and the registry that Stacy just spoke about, and something that will probably involve periodic assessments over time when you come in to see your neurologist or your orthopedist. And so be on the lookout for that. We encourage you, as Stacy said, enroll early, enroll often, enroll everywhere. It really helps and supports the research effort if you're involved in as many things as possible. Don't worry about competition, because we all want to synergize and work together. And we have ways of anonymizing your names and birth dates into random numbers that we can share to make sure we're talking about the same person, so we're not duplicating efforts. So just a general comment on that. Thank you.
Thank you. Are there any other questions related to the work at the Lawler Lab?
Axel from Sweden, with a daughter of who has TPM2, but I was interested in your work with like the mitochondrial dysfunction. Is that something you found only in mice, or is that found in humans as well, or is that not confirmed?
No, we're just deciding who's saying what. So we haven't really looked that much in the human tissue yet. Right now we're mostly focused on the mice, and that's exactly, we're not super far on this project by any means, like we're just starting it. So we literally got that proteomic data back, those protein analyses back like maybe 2 months ago. So Becca's been plugging away just looking at that, and we're still trying to identify certain biomarkers and certain pathways of disease to really narrow down on what to look for in the human tissue, because it's still limited amounts of human tissue. Obviously, none of the biopsies are super big, so we want to make sure that whatever we're looking for, we actually know what to look for before we just randomly go digging around in humans. So with that, we're making progress. We have identified a few biomarkers between the different mouse models, and Becca, if she wants to say anything about that, she actually looked at some of the human tissue for those same biomarkers with just protein aggregation.
Yeah, so what I was doing with the human tissue and biomarkers is trying to identify which mouse models act like which humans, because as we know, even people with the same gene mutation can act very differently. And so I found a few biomarkers, which we don't have the data here at all, that specifically mark nemaline rods in one of the mouse models. And so I compared that against human tissue and actually across mutations. So I only analyzed 10 different samples, but one patient with an ACTA1 mutation and one with a NEB mutation who showed the same biomarkers as the ACTA1 H40Y mouse model, which suggests that they could potentially act the same. So another part of my project is to look at those patients who have the same biomarkers, and we have some of their de-identified clinical data, and we can see if they act the same way. And then in reference to the actual mitochondria in human tissue, we have looked at some electron microscopy, which have shown mitochondrial abnormalities in the human tissue. So either fragmented mitochondria or aggregates of mitochondria, and so this suggests to us that it could be a process that is under-recognized in NM right now.
Okay, great. Thank you so much. We're going to move on to the next group just to try and keep with our schedule. Thank you so much for your presentation.